Welcome to Microlecture 48. We're talking about another alkene addition reaction here, oxymercuration-demercuration. Okay, so we're going to be covering the addition reaction of water to alkanes, but this one is done a little bit differently than the dilute solution of H2SO4. This time our reagent set is mercury diacetate. And like before with the other reactions of alkenes, we want to be able to show a curved arrow mechanism. This time explicitly just for step 1, the oxymercuration step, so not the step 2, which is a demercuration step. And in addition to the mechanism, you want to be able to predict the products with correct regiochemistry and correct stereochemistry. So let's do a few examples here of just kind of predicting the products. All right, so the reagent set that we're using here looks like this. It's mercury diacetate in water, and that's step 1. And then step 2, so this is the first time we're seeing this. When you have reagents separated by numbers, it means that you can't add everything all into one pot. It's not what they call one pot, right? So whatever I have here written here in step 2 cannot be added in there with the mercury diacetate. We have to bring that reaction to completion first and isolate the product, and then we can go ahead and add the reagent set from number 2, which is sodium borohydride, NaBH4. Okay, so you'll identify this reagent set. It'll always be written out like this: mercury diacetate in water as step 1, and sodium borohydride as step 2. And so we'll be predicting how water adds across the double bond, and what we're going to find is that the regiochemistry is very similar to that of adding a dilute solution of H2SO4. So OH is going to add to one carbon, H is going to add to the other carbon, and the OH does add to the more substituted side. Okay, we'll think about stereochemistry. If the product were chiral, I would have to, be careful how I represent the product. I wouldn't want to show that just one stereoisomer forms, because a mixture of stereoisomers can actually form. So in this case, it's achiral because there's no stereocenter. So since there is no consequence with regard to stereochemistry, I'm not worried about drawing in dashes and wedges. So another example might look like this. So I've got my mercury diacetate in water, and then in step 2, sodium borohydride. So again, I'm going to predict that the OH adds to the more substituted side of the carbon-carbon double bond, and H goes to the less substituted side of the alkene. So those two are very similar, and let's do one more that throws in a little bit of complexity. Move those up out of the way. And so our last one looks like this. And what we're going to predict there is that the OH adds to the more substituted side, as you might have guessed, based on its similarity to the reaction with dilute H2SO4. Okay, thinking about stereochemistry of both of these, I don't see a stereocenter, so that major organic product was achiral, and we didn't really care about making sure we were drawing dashes and wedges. Whereas this one, we're going to have a 50-50 mix of possible stereochemical outcomes, because we do have a stereo center, and so the methyl could be on a dash, or or a wedge. And the alcohol likewise could be on a dash or a wedge. So I'm going to draw both possibilities. And for that reason, since it's a 50-50 mix, it is achiral. But it's because it's a racemate, not because it doesn't have a chirality center. All right, so the mechanism for this reaction is important to understand, at least the first step of the mechanism. So let me use a fairly simple compound, maybe something like this, and show how, this mercury diacetate looks. So this is a mercury that is connected to two acetate groups. In other words, it looks like this. Okay, and so what's going to happen is, just like with all of the other alkene reactions, the carbon-carbon double bond is the nucleophile that's going to start the reaction by attacking an electrophile. The mercury is a very partially positive center. It also happens to have some electrons available to circle back around and attach at one of the two carbon atoms of our alkene. So we see the alkene attacking as a nucleophile, and then the mercury atom turning around and forming a bond back again to the other carbon of the carbon-carbon double bond. So I see two bonds to mercury forming simultaneously here. And then one of the two acetate groups is kicked out as a leaving group. So what just happened there was that we formed what's called a Mercurian Intermediate. So Hg is bonded on both carbons of what was the alkene. Right, and so it's still attached to one of the acetates as well, and the mercury now bears a positive charge, and this is a pretty funky looking intermediate, but it's called a mercurinium. And so notice that we do not form a carbocation here, and so we do not get any carbocation rearrangements. So I'll say no carbocation rearrangements. Okay, so you might have been thinking, why would we do this chemistry instead of dilute H2SO4 if we get the same regiochemistries and stereochemistries as final products? Well, if there is a situation where we don't want a carbocation to rearrange, then we can use this reagent set and limit the possibilities of these undesirable products that would form otherwise formed through carbocation rearrangement. So the last part of the mechanism involves water coming in and attacking, and it is going to choose the more partially positive carbon atom, and the more partially positive carbon atom of the two that are bonded to mercury is going to be the one that would form a more stable carbocation. In other words, more substituted. So this is why we end up with the same regiochemistry, but we don't go through a carbocation intermediate, and so it doesn't have the opportunity to rearrange if it could. And so the bond from oxygen to carbon forms, and the electrons are kicked off back onto mercury, and the structure kind of opens up, and we end up with the second intermediate, and I'll draw it down here. So now we have mercury, and that's attached to an acetate group, and we have positive charge on our alcohol, essentially, what will be our alcohol. So all of that is what the intermediate looks like here, and in the last step, we lose a proton from the OH2 group to form the alcohol, but we also lose the mercury, And so a hydrogen atom from sodium borohydride displaces the mercury acetate. All right, and so for that, there's going to be no mechanism required of you. You don't have to know how to push any electrons or draw curved arrows for that. So just be able to predict the product from here, and that's going to look like this. Okay, remember that if you form a stereocenter, you want to be able to show that we get both possible stereochemical outcomes. That is to say that the water here at the beginning of this mechanism, the water can approach from either face of this intermediate, from top or bottom, with equal likelihood, because it is a planar intermediate, and so we get water adding in from the front and from the back, giving us both possible stereochemical consequences.